Okay, hello everyone. In this video, we are going to discuss one of the most important topic belongs to Laplace transform, that is your convolution theorem or Laplace transform of convolution of two functions. In our last class, we have been discussed in detail about Laplace transform of a periodic function. Regarding that, we solved a numerical, and I given one numerical for you that you have to do by yourself. Hopefully, you don't. And today we are going to discuss convolution theorem. Here is the statement that if Laplace transform of f1t equal to capital F1s and Laplace transform of small f2t equal to capital F2s, then Laplace transform of convolution of two functions f1t and f2t will be equal to capital F1s into capital F2s. So here proof starts. In general, the convolution of two functions f1, fx and gx is nothing but 1 by 2 pi root over minus infinity to plus infinity f of u is the another variable, g into x minus u du. May you remember we discussed when we discussed about Fourier transform, convolution theorem of Fourier transform. At that time also we discussed that convolution between two functions. Here convolution means coupled with each other. This f and g both are coupled with each other will be equal to 1 by 2 pi root over minus infinity plus infinity f u g into x minus u du. This is the proof you can found in your mathematics honors syllabus. Here it is not required. We are going to be use this one. Okay, and uh, also we can found that the convolution of the two functions, suppose f1t and f2t, will be written as f1t convoluted with f2t will be equal to 0 to t. Here 1 by 2 pi root over minus infinity plus infinity. Instead that only 0 to t, f1x is the another variable like u into f2t minus x dx. So some books are written in this format and some books also written in this format. Both can be proved. The proof is not in our syllabus, that is your mathematics honors syllabus. Okay, so here Laplace transform of this one convolution of the two functions f1t and f2t is equal to Laplace transform of this one will be equal to f1 capital F1s into capital F2s. That implies Laplace transform of convolution with the two functions will be equal to, here Laplace transform means 0 to infinity e to the minus st, this one, this function, entire function 0 to t integration f1x into f2 t minus x dx dt will be equal to f1 capital F1s into capital F2s. What we intend to prove, let this is your equation number 1. Okay, so from equation number 1, the two limits of integrals of above equation number 1 lie in the first quadrant. Here 0 to t all are positive, 0 to infinity all are also positive. That means all the limiting values are in the first quadrant between two lines x equal to 0 and x equal to t. So here this is the variable, this is the integration from with respect to x and varies from 0 to t, right? So like, right, so x varies from 0 to t, x varies from 0 to t. That means if we are going to consider this figure, x equal to 0 means this line. If here say along this axis we consider the variation of t, along this axis we consider the variation of x. Okay, so obviously this line will be the equation of x equal to 0. See, if we are going to consider this is our x-axis, this is our y-axis, then this is nothing but y equal to 0, equation of the x-axis. This is your x equal to 0, equation of y-axis. So along this, if we consider the variation of t, along this we consider variation of x, then this line is nothing but, the equation of this line is nothing but x equal to 0, and x equal to t is this line which is inclined 45 degree with this axis. So from this equation number 1, so here we found that the first quadrant in between the two lines, this and this, x equal to 0 and x equal to t. So in between these two lines, all the variables we can found and we are going to be integrate. So from equation number 1, first we have first integration will be done with respect to x. So first integration with respect to x, then with respect to t. Then integration will with respect to x with the limits x equal to 0, to x equal to t. Then with respect to t with t equal to 0 to t equal to infinite. Same thing it has been written. Then integration will be done with respect to t with the limits t equal to 0 to t equal to infinite. I refer to the figure 1. This is your figure 1. Now consider change of order. Change of order of integration, that is the first integration will be done with respect to t, then integration will be done with respect to x. So here first integration done with respect to x and then t. If I consider the change of order, then first integration will be done with respect to t and then with respect to x. So here I am going to uh, explain what is the figure exactly explaining to us. Here you can see 0 to t with respect to integration with respect to x, limit 0 to t. Okay, so consider this strip. Okay, so this strip lower limit is x equal to 0, upper limit is your x equal to t. If we are going to consider this strip x equal to 0 lower limit, upper limit equal to x equal to t. If I am going to consider this strip, this one, lower limit x equal to 0, upper limit also x equal to t. So this strip will be starts from here and moved up to infinite. Okay, so these strips starts from 0 and moved up to infinite. So that means if I will be add or integrate these strips, then I can say that I can found the integration of this entire area. Likewise, the integration 0 to t with integration limit 0 to t with respect to x, that means this strips. Then integration 0 to infinite with respect to t means these integrations starts from 0 extended up to infinite. That means your t starts from 0 extended up to infinite. Okay, this is the first integral and corresponding figure 1. Now we are going to consider the change of order. That means first we are going to integrate with respect to t, then we are going to integrate with respect to x. So equation number 1, the so-called double integration, can also be done by change of order of integration. That is, first integration will be done with respect to t, which whose limits changes from t equal to x to t equal to infinite. Then integration will be done with respect to x with limits x equal to 0 to x equal to infinite. First I am going to explain this figure, then we are going to go for the derivations. So this is your figure 2. Here you can see in our figure 1 we consider the strips, vertical strips. So vertical strips means lower limit x equal to 0, upper limit x equal to t, varies from t equal to 0 extended to t equal to infinite. Now I am going to consider the horizontal strips. I not change the variable variations along this axis. I consider the variation of t. This is same with figure 1 itself, variation of t along this axis, variation of x. This is also same with this figure. So here you can see horizontal strip. If I am going to consider, t changes from t equal to x to t equal to infinite. if I am going to consider this horizontal strip, t equal to x to t equal to infinite, t equal to x to t equal to infinite. So here you can see, if I am going to consider a strip at here, if I will consider a strip at here, here I am drawing for explaining. You should not write, you should not draw in your note. You know, note only 3 strips you have to draw. Okay, so here if you are going to consider this strip, t changes from x to infinite. X changes from, here you can see, x changes from x equal to 0 to x equal to infinite. So if I am going to consider here x, then x equal to 0 to x equal to t, but it is not the if I am going to consider here the change of x, then x equal to 0 to x equal to t, but it is not giving the proper answer, because the extension of t is from t equal to x to t equal to infinite. So here at the end, if I am going to consider x variation, the x variation will be x equal to 0 to x equal to infinite. Okay, so in this way we changed the order of integration. First we are going to consider the integration with respect to t varies from t equal to x to t equal to infinite, then with respect to x, where x varies from 0 to infinite, as shown in figure what I explained. Now hence equation number 1 will be written as equation number 1 can be written as Laplace transform of convolution of the two functions f1t, f2t will be equal to, here in equation number 1, t changes from 0 to infinity. So here 0 to infinity x changes, and t changes from x to infinite. So here you can see f1 is the function of x only, but f2 is the function of t and x. Only for that, f1x taken outside of this integration and integrate with respect to x. But here you can see e to the power minus st and f2t minus x, both are function of t, so will be will be inside the integration of t, whose limit changes from x to infinite. Now, by considering the change of order, we have been written like this, that 0 to infinity f1x integration with respect to x, then integration with respect to t varies from x to infinite e to the minus st into f2 t minus x dt. So first integration we are going to consider this one, then we are consider with respect to x. 0 to infinity f1x into x to infinity e to the power minus s t minus x plus x. Here I subtracted one x and added another x, f2 t minus x into dt and dx. 0 to infinity e to the power minus sx. Here you can see e to the power minus s into x1 term will be come up, which will be the function of x only, can be taken outside. This is the e to the power sx into f1x, which will be integrated with respect to x, and with respect to integration with respect to t is written inside this bracket, limit x to infinity e to the power minus s t minus x into f2 t minus x dt. 0 to infinity, I separated these two integrals like this, e to the 0 to infinity e to the minus sx into f1x dx into 0 to infinity e to the minus sz into f2z dz. How? Here we consider z equal to t minus x. So dz will be equal to t if we are going to consider the limit here for the t, when the t equal to x, so obviously here if I will put x, z will be equal to 0. If t will be infinitive, if I will put infinitive, so z also will be infinitive. So limit changes from 0 to infinity e to the power minus sz into f2z dz. Here both x and z at the dummy symbols can be changed to another variable t, or another symbol to t. So hence we can write Laplace transform of convolution of the two functions f1 and f2 function of t equal to 0 to infinity e to the minus st. Here x changes to t f1 t dt, 0 to infinity e to the z changes to t into f2 t dt. So that implies Laplace transform of convolution of the two functions. This is nothing but Laplace transform of f1t. This integral is nothing but Laplace transform of f2t. So that implies Laplace transform of convolution of the two functions is equal to f1s, capital F1s. This can be written as capital F1s. This can be written as capital F2s. This convolution of the two functions can be written as Laplace transform of 0 to t f1x, another variable x, into f2 t minus x dx. Here also same thing it has been written. This one will be equal to f1s, capital F1s into f2s, hence proved. This theorem is most essential for your exam point of view. Not often, always this theorem asking in your exam for 6 marks. So practice it for your exam. Now we are going to go for the numericals using convolution theorem. Find the Laplace transform of 0 to t e to the power x sin t minus x dx. This numerical we are going to solve using convolution theorem. We know, according to convolution theorem, Laplace transform of 0 to t f1x f2 t minus x dx equal to f1s into f2s. Let this is your equation number 1. Comparing equation number 1 with given question, if I will compare this one with respect to this one, then so-called f1x, this one is nothing but e to the x, and f2 t minus x is nothing but sin t minus x. So hence the answer will be f1s and f2s. Here f1s is nothing but Laplace transform of f1x. As per the question, this f1x is e to the x. Capital F2s is nothing but Laplace transform of f2t. Here f2t minus x is nothing but your sin t minus x. If I will consider only f2t, the function will be only sin t. So hence answer will be Laplace transform of e to the x into Laplace transform of only sin t. This one only sin t. So we know that Laplace transform of e to the t equal to 1 by s minus 1 into sin t Laplace transform 1 by s square plus 1. This will be the answer. Okay. So here you can see that e to the x I have been written over here. Here I written e to the t. See, this x and t are the dummy symbols, can be changed. So only for that I have also clearly written over here. Okay. Next question is that find the Laplace transform of 0 to t e to the minus ax into e to the minus b t minus x dx. So comparing this theorem, 0 to t into f2 t minus x dx, Laplace transform capital F1x into capital F2 x. Here f1x the Laplace transform of f1x, small f1x, but f2s is the Laplace transform of f2t, right? So if I will compare this with the question, so f1x equal to e to the power minus ax and f2t minus x equal to e to the minus b into t minus x. So obviously Laplace transform of now f1s is nothing but Laplace transform of this one, and f2s capital is the Laplace transform of f2t. Here f2t is your e to the power f2t minus x e to the minus b t minus x. So f2t only means e to the minus bt, e to the minus bt. So both x and t are dummy symbol. It can be changed to another symbol So here I changed x to t. So e to the power at, here e to the minus bt, Laplace transform. We know the Laplace transform of e to the at is nothing but 1 by s minus a. So here a is nothing but minus a. So 1 by s plus a, this will be 1 by s plus b is your answer. Okay, so here we are going to stop our today's discussion. Next class we are going to start inverse Laplace transform, right? So thank you so much for watching this video. Thank you.